On this page, we'll be talking more about random assignment and experiments in general, but we'll be looking at new terminology as well and defining things. So it'd be a good idea to kind of write some of these down if you haven't already, if you haven't seen them. But let's summarize what we know about experiments so far. So first, the goal of the experiment is to provide evidence for a cause and effect relationship between two variables. If researchers are just interested in proving an association between two variables, then you can just use an observational research, right? But if you want to prove cause and effect, one variable causes another, then we're going to need to do an experiment. And a well-designed experiment controls the effects of confounding variables so that they can isolate the effect of the explanatory variable on the response. Two commonly used methods, as we've kind of talked about in the last page or two, for controlling those effects of confounding variables are direct control and random assignment. So direct control, the example that they used was that they wanted to see which hand drying method worked the best in public restrooms. And the direct control was they wanted to make sure that there was the same amount of bacteria on everyone's hands. So they had them handle raw chicken for the same amount of time, and they made sure that they used exactly the same amount of soap, and then they washed their hands for the same amount of time. Those were their direct control elements. And then random assignment, the example we saw was children that were assigned to two different groups. They all had to get hernia surgery, but they were going to be assigned to two different types of hernia surgery. That would be an example of random assignment. So I think mainly you want to understand all these terminologies enough to where if you were given a new scenario, could you identify what the random assignment was? What are our direct controls? So that's really what terminology is. You want to be able to identify them if you're given just a new experiment situation. I guess that's what you might see in the quizzes. Okay, random assignment uses random chance to assign participants to treatments. We saw that. It creates similar treatment groups. That way we can be confident that any differences we observe in the response of treatment groups, it's due to the explanatory variable and not any confounding variables. So that way we can for sure prove that there's a cause and effect relationship. So from here we'll discuss more strategies that are commonly used and more kind of terminology as I mentioned. Let's see. So because we want to observe what would happen even if what we want to happen in the response variable, it might have happened anyway. So what if you just give something a little bit of time? Okay, I'm going to give these people or this animal or whatever a little bit of time. Maybe what we're hoping to be the response variable actually changes and happens the way we want it. But what if it's not due to what we think is the explanatory variable? What if it's just something that was going to happen anyway? So that's what they're saying here. And for that reason, if that's a concern in a particular research experiment, it's important to include a control group. So you've probably heard it talked about control groups if you've ever read about different studies. But a control group is a group that receives no treatment. That way, if there is a change observed in both groups, the group that is getting a treatment and then the control group that's not getting a treatment, if both of them have a change in the response variable, then you know that this change was going to happen regardless of what you think is the explanatory variable. But if the first group changes, the one that's actually being acted upon, and the control group does not change, then you know it had to be because of the explanatory variable. So as I say here, the control group provides a baseline for comparison. So below we'll talk about an example of a control group. Let's see, music and rats. So this person wanted to examine the relationship between music and the ability of rats to run a maze. So that's kind of interesting. It either affects it as it makes them go faster or do better, or hurts them, I guess. He had 3 treatment groups: exposure to music by the heavy metal band Anthrax, exposure to music by Mozart, and no exposure to music. So that would be the control group there, the one that had no music. With a month of practice, so the rats should know how to do this maze. They had been practicing for a month. The rats in all the groups would probably get faster at running the maze, right? The control group provides a baseline for the comparison, as we said. At the end of the month, the rat in the Mozart group were much faster at running the maze than were the rats in the other 2 groups. So in comparison, the rats that listened to Mozart did the best, and then the ones that didn't listen to anything, or the ones that listened to the heavy metal band Anthrax, didn't do as well as Mozart group. Comparison to the control group shows that the improvement in the Mozart group is not due to the rats being more experienced with the maze. It just has to do with Yeah, the type of music being listened to. So then, and then the other example, the hernia treatment example from the previous page, researchers compared two different surgeries. The response variable was recovery time, so it would not have made sense to have a no treatment group. Yeah, the whole point is to prove that people being treated with different things recover faster. So there would be no control group. Yeah, in this case, people have to be treated. That's what they're trying to prove, that one type of treatment is better than the other. But one type of surgery was the standard treatment for hernias, and children who received the surgery represent the control group. So since they're trying to prove that a new type of surgery may or may not be better than an old type of surgery, I guess the control group is the children who are getting the old type of treatment. They're just the standard type of surgery that they would always get no matter what. So since they're not really changing anything, they're not introducing a new type of surgery to those children, that would be the control group. They provide a baseline for comparing recovery time. Okay, now we'll talk about kind of a new topic or a new phenomenon that is often seen in groups of people in experiments. So when there's human participants, the use of a control group may not be enough to establish whether a treatment really has an effect. A substantial amount of research shows that people respond in positive ways to treatments that have no active ingredients, a response called the placebo effect. A placebo is a treatment, this is probably worth writing down. A placebo is a treatment with no active ingredients, sometimes called a sugar pill. So you've probably heard of that before. If someone believes that they're being treated with medicine, then their body or their brain, or I guess think no one really understands the phenomenon, but their body kind of heals itself just because of the power of belief. So even if you're giving someone just, a pill that's made of sugar, it's just a big piece of sugar, and you tell them it's a medicine to help them with something, a lot of times they actually get better on their own. It's not because of the pill, obviously, because it's just sugar, or maybe even less interesting than that, made of flour or something like that. But it's due to something else. So that's one thing that researchers have to worry about as well. Like we said, called the placebo effect. So here's an example of the placebo effect in medical experiments. So after thousands of studies, hundreds of millions of prescriptions, and tens of billions of dollars in sales, two things are certain about pills that treat depression. Antidepressants like Prozac, Paxil, and Zoloft, they actually work, but so do sugar pills. A new analysis has found that in the majority of trials conducted by drug companies in recent decades, sugar pills, or placebos, have done as well as or better than antidepressants. The new research may shed light on findings such as those from a trial last month that compared the herbal remedy St. John's wort against Zoloft. St. John's wort fully cured 24% of the depressed people who received it, and Zoloft cured 25%. But the placebo fully cured 32%. So how do you explain that, right? That's amazing. The placebo, which is nothing, it's just a sugar pill, just because people believed it was a real treatment, it did better than Zoloft, which is actually a real treatment, and then St. John's wort, which is like, I think that's kind of sort of like a vitamin, I guess, type of thing. The placebo effect can confound the results of medical experiments. It's uncertain what is behind the placebo effect, because people believe in medical experiments and that they improve when taking a placebo. The placebo group provides a baseline for comparing treatments. We cannot eliminate the placebo effect on a treatment group. So what do researchers do in that sense? But the placebo group and the drug group experience the placebo effect. If a treatment produces better results than a placebo, then we have evidence that the treatment and not the placebo is responsible for the improvement. So with those antidepressant medicines, you might say that just believing that something's going to help them actually helps patients more than an actual medication, because what they say over there that 32% of those that had the placebo actually felt better. So that's what they said up here, versus 25% who actually got the medical researcher or the scientists created pill that was supposed to help. That's a pretty significant difference, I'd say. 32% versus 25%. That's 7% of people. Wow. And here we talk about, we've used this terminology, I think, before. If you have already written this down, then, just don't worry about it. But if you haven't written it down before, it's probably a good idea. In experiments that use a placebo, participants don't know whether they're receiving the drug or the placebo. Because if they knew, of course, that they were receiving a placebo, they wouldn't believe that it's going to work. They would believe it's not going to work. So we want to make sure that they're what they call blind. Participants are blind to the treatment to prevent their own beliefs about the drug from confounding the results. So here's an example of blinding. Let's see. if you remember, a previous example we went over was women when they're going through menopause. Some received a hormone replacement therapy, and there were claims that it was working and it was helping people, and it actually lowered the rate of, was it heart disease, I think? And then in fact later we found that it was the opposite. Women that took the hormone replacement therapy, actually their health deteriorated a lot faster than those that didn't. So in this experiment, researchers randomly assigned 16,000 women to one of two treatments. One group took hormones, the other took a placebo. So the women were blind to it because they thought that it was actually a real treatment. And this experiment was in fact double blind, which if you remember from before, that means that neither the women receiving the treatment or the placebo knew if it was a placebo or the treatment, but also the researchers didn't know if they were giving the placebo or the actual treatment. In a single blind experiment, one of the two, either researcher or participants, do not know which treatment the participants receive. That's only single blind, or either the participants, or the researchers. One of them knows what they're getting. Let's consider one last question. If an experiment is well designed, can we generalize the results? So how about in the hormone experiment? This experiment has all the features of a well-designed experiment. First, a large number of participants, 16,000 women. That's quite a few, I'd say, relatively, compared to the number of women in the United States, I guess. They used a placebo group like they were supposed to. That's one of the main things you want to do in these types of experiments. Random assignment of women to hormone treatment or placebo. Yeah, they weren't choosing a certain type of woman to go to one or the other. Like, when it was in the beginning, they said that the women who took the hormone replacement therapy, it was probably because they were more wealthy, they had better access to healthcare, stuff like that. So that would not be random assignment. It would be the wealthiest women take it and the ones that maybe aren't as wealthy don't take it. That would not be random assignment. But later they did a study where there was random assignment, and then there was a double-blind design. So the women getting the placebo or the actual treatment didn't know whether they were getting the placebo or the treatment. After 5 years, the group taking hormones had a higher incidence of breast cancer and heart disease. Unfortunately, researchers were so alarmed by the results that the experiment was ended early to prevent further harm to the health of women. As a result of this experiment, the use of hormone replacement therapy fell by 66%. I would have thought it would fall more than that, but okay. Yet the British Menopause Society and the International Menopause Society questioned this reaction. The Women's Health Concern, the Women's Health Concern, a British nonprofit group that provides an independent and unbiased information about women's health, wrote, quote, "It must be remembered that the WHI data on which the concerns were raised relative to overweight North American women in their mid-60s, and not the women that are treated with HRT, hormone replacement therapy, for their menopausal symptoms in the UK, which are usually around the age of menopause, namely 45 to 55 years. So, end quote. The concerns expressed here do not challenge the validity of the results of the WHI experiment, but instead they question whether the results apply to a larger group of women, those that are younger and not overweight when they go through menopause. So I guess it sounds like the original experiment was done on women in their mid-60s, when really women that go through menopause initially are a little younger. They're supposed to be, what they say here, 45 to 55. But these people were saying that they were the ones that were experimented on were done in their ages were in the mid-60s. So that's maybe not as applicable to everyone, all women, as they thought it was. So now we know that in an experiment, we intentionally manipulate the explanatory variable to observe changes in the response variable. We use the explanatory variable to create different treatments. If we see different responses in the different treatments, we want to be able to say that the differences are the result of the explanatory variable and not any other confounding variables. We must rule out other possible explanations for the differences we observe, so we use direct control and random assignment, as well as a control group, a placebo group, or blinding or double blinding as appropriate. But none of these strategies will rule out the influence of chance variation. So I guess that's a big difference between statistics, this type of math, and then other math, algebra, geometry, all that stuff. You can't really necessarily see its application in real life, right away. Sometimes there's word problems, but overall you don't see the applications in real life. But it's very exact, it's always, this is the exact answer, this is right, this is wrong. In statistics, it's more like in social sciences, I guess, like psychology and stuff, where, you don't feel like there's an exact answer. You just researchers do their best and they come to conclusions, and maybe in the future we see that, oh, those conclusions were actually wrong, but we do our best. We can't, yeah, like they said, we can't influence chance variation. We randomly assign participants to treatments and we produce similar groups most of the time, but there's always a small chance we'll end up with a treatment group that's not similar, and maybe you don't even know it, you don't realize it. So for example, in the hernia experiment with children, we saw the random assignment creates two groups. The ages were pretty close, but there's a very small chance that we could get two groups with that significantly different age. Because if you just keep randomly assigning over and over and over, the chances are that once or twice you might get groups that are the average ages are pretty far apart, just because of chance and probability. It wouldn't happen very often, but it could. And if it does happen, the results of our experiment are confounded by age. Now, so in a similar way, when we investigate how well a random sample estimates the proportion of students receiving financial aid in a population, we saw that the proportions from random samples gave good estimates most of the time. But once in a while, a random sample did not give a good estimate. Larger random samples varied less, but it still varied. So here our main point is just that good study design is important, but it's not always perfect. Random selection and sampling can control bias. Random assignment in experiments can control the effects of confounding variables, but there's always a small chance, like they say here, even when we randomly sample, that the results we observe in a poll do not represent the population well. It's usually on accident, but once in a while, researchers want a certain conclusion, so they'll make sure that happens by, quote unquote, randomly assigning, but really they're not randomly assigning. They're getting exactly what they want because they want to see certain results. But similarly, there's always a small chance, even when we use random assignment, that the differences we observe in an experiment are due more to random variation and not the explanatory variable. So for this reason, we have to understand how random chance behaves. This is the role of probability. We'll study probability later in this course before we learn more formal statistical methods for determining what we observe that could be the result explained by a chance.